In this section, we now focus on process of implementing spatial information science to formulate a space-related problem and its justified spatial solution. The theoretical and technical knowledge provides a foundation which helps in executing spatial information projects. Here we examine a framework for the development of some spatial information science applications which we have already practiced and are familiar with. The emphasis is on the practical aspects of designing and managing a spatial information science application. The design techniques help us to identify the nature and scope of a problem, define the system to be built, quantify the amount and type of data which is required, and indicate the data model needed for the analysis which is required. The project design and management approach here can be suitable examples from small-scale spatial information projects. The type of project which may be required by a spatial information course or as a part of a research project execution. The approach does not embrace any specific design methodology or management philosophy, but it is an integration of spatial ideas which you have learned through this course, which may have been learned during the course of this study. Now it is the time for its execution. Various elements of the approach, when scaled up, could provide a methodology for the implementation of larger projects which in future you may carry out. Any design and management approach adopted should be adapted to meet the needs of the application, the available technology, the users of the system, and the organizational culture in which these spatial information science must reside. So that is the framework on which we would be now trying to sensitize you as to how you can carry forward your own individual project depending and based on the learning which you have completed through this course. Here we start by considering how the character of the problem for which a spatial information science solution is being sought that can be identified. Two methods are introduced: the rich picture and root definition. A method for constructing a spatial information science data model is then discussed. A distinction is made between the conceptual data model and physical implementation of this model in the system, the computer system. The cartographic modeling is then considered. It is an approach for structuring the spatial information analysis required by whoever is pursuing this. A review of some project management approaches and techniques and the tools available for the implementation of a spatial information project is also discussed in the later part. Further, implementation problems and project evaluation are also considered in this particular section. So, to begin with, first the problem identification drawn from the soft system approach to system design. Here the soft system idea, which was developed, as you might be aware, by Checkland in 1981, this soft system approach to problem identification provides a method for addressing unstructured problems, which is very useful in GIS and spatial information science context, because many of these GIS or space related problems are unstructured, and to my mind I would say often they are difficult to define, as it might happen in many of the pure science disciplines. This spatial information, which is based on the various phenomena, various attributes, so it is difficult to structure them. And in that context, this soft system idea is quite relevant in spatial information science research. To formulate a problem, users should appreciate the context or worldview from which the problem is being considered. I mean to say here, the man-nature relationship, the interaction of human being with all kinds of phenomena which are existing around them. The soft system models are abstract logical models that help with our understanding and structuring of a problem. Another is developing a root definition, which I would say a statement of an individual's or group's perspective on the problem. The rich picture, it is another important dimension to the project management in spatial information science. The rich picture is a schematic view of the problem a project will address. It presents the main components of the problem as well as any interactions that exist. This may include crossroads, it is the term which has been given. The symbol crossroads symbol expresses conflict. It is used to indicate the differences between the phenomena which are in close proximity and compete with each other. There is conflict since the reason of the two groups for system development are different. So that is one option. The second is, and again a very different kind of term which I am using here. It is known as eyes. They are used to represent external observers which observe and evolve opinion about the emerging issues and solutions also as outside stakeholders. Another can be speech bubbles. It may be personal or group opinions. They are indicated in speech bubbles. The different priorities for attaining objective is evolved to direct the system. This way, the rich picture records thoughts on paper and helps to organize the unstructured ideas. For a small-scale project, the rich picture may be drawn by one individual. A rich picture drawn by a project team will represent a consensus view of a problem reached by all the project participants. Now coming to the root definition. Like rich picture, the term root definition also comes from the soft system approach. The root definition is a view of a problem from a specific perspective. Different users have different views of a problem. The views of groups involved in design process might be quite different and lead to a degree of conflict also. So the system developer must get these two groups to agree on a common root definition. Establishing a common root definition for a problem will help others to evaluate, understand why a spatial information has been constructed in a specific manner in a particular way. Likewise, understanding that others may view a problem from a different perspective that will ensure a spatial information application as designed to address a range of needs. If a single root definition can be agreed upon, then there is a great chance that spatial information science will meet the requirements of all concerned. Once the rich picture and root definition exist, the main aims and objectives for a project can be identified and a spatial information data model can be created. If it proves difficult to draw a rich picture or formulate a root definition, then the problem being addressed may be unstructured, and unstructured problems, as I have said earlier also, are are very difficult to address, but this also happens in spatial information science projects. So, beginning a data model. The rich picture and root definition that define a problem turn into a spatial information data model. You look into this particular slide and you will have a fair idea as to how we can design a data model and what is the process, how we proceed to carry out any project. Now here the term data model is used as a collective term for the process of identifying all the design elements used in the construction of a spatial information. It offers a useful solution to this confusion by distinguishing between conceptual and physical data models. The conceptual data model is a high-level view that is independent of the system, computer system. This is the user's view of a problem and it carries many elements into it. The physical data model, on the other hand, describes the organization of data in the computer. Therefore, from the project design and management perspective, it is useful to think of the spatial information data models as consisting of two parts, a conceptual model and a physical model. The conceptual data model adds spatial detail to the rich picture by including elements of spatial form and spatial process. The physical data model is concerned with how to represent the conceptual model within the system, within the computer system. Now, details about the spatial data model, you might recall we discussed it at length about raster and vector model. So the spatial data model, raster or vector, the appropriate data structure and the analysis scheme are included in the physical data model. The data modeling stage is frequently neglected in the design, and insufficient attention to data modeling may lead to the failure of spatial information project that will be unable to meet the expectations of the users. Now, another can be conceptual and physical data models. One way to create a conceptual data model is to borrow from the ideas of hard system analysis. And hard system analysis advocates the clear identification of the elements of the data model. That can be the entities, their states and their relationship to each other. One method of presenting this is using a flowchart. In system analysis, flowcharts use a range of symbols to communicate different aspects of the model. Here, technical spatial information terminology can be avoided also when constructing the conceptual data model. This is a better idea as the resulting flowchart will explain what it is, the spatial information application, and how it will do in a way that is clear, that should be clear to all, everyone. So if we use technical terms, then some individuals who would be part of the project may not understand that. So effective execution of the project, it's a better idea. So for project design and effective management, it requires logical structuring of database that contain geographic information and other related attribute information which comes from physical world as well as social economic world also. So you can see that how the spatial information science paradigm is being conceptualized and represented in this diagram. So this, along with effective combination of hardware and software components for efficient automation of voluminous geographic data handling, and also a management environment that provides resources and enables changes to be made for incorporating the GIS utilization, spatial information utilization within the organization. Now, the hard system analysis in spatial information advocates trying to understand reality by rebuilding part of it. The GIS data models or spatial information data models attempt to reconstruct part of the reality for specific purposes, depending on our objectives. The hard system approach was the dominant methodology used for the design of actually the computer systems and the softwares also. There are three important terminology of the hard system approach. These can be said as entities, the states, and relationship. If we take first the entities or elements of any system, they can be, as I am saying, they can be either physical or even conceptual also. In GIS and spatial information terms, entities are represented through point line areas. These are entities which are represented in spatial information in the form of point information, point entities, line entities, and polygon or area entities. It can be added with surfaces also, and also networks. So entities also possesses properties known in hard system term as states. And in spatial information terms, states are attributes. So we talked about the entities, point line area. Now we are talking about the entities, which in spatial information term we are calling it as states. So I am saying that states are attributes. In addition to relationship exists between entities, in spatial information this relationship could be the topological links between the features. So that's an interesting aspect of spatial information. Topology, if you recall, I have mentioned that the arrangement of these entities are in specific manner and they create a topology in space. In that connection, I would say that there are four phases in hard system analysis. The first one can be the lexical phase, which is to identify the nature of the application, the study area, defining the real-world features of interest, and associated attributes which are related to the real-world features, which is under investigation. The another phase can be said as the describing phase. The relationship between entities and group of entities are defined here. So that explanation would be known as the describing phase. The third can be the modeling phase. Now, spatial information is used to address the problems identified during the lexical phase, the first phase. The way in which entities and their states, the relationship, attribute relationship, will interact and respond under differing situation is expressed in this modeling phase. And lastly, the analysis phase. Now, this phase is the validation of the modeling phase. So what we are pursuing in the analytic part within the modeling phase, this phase, the analysis phase, is the outcome of it, where we are validating the modeling phase. Testing occurs to find out how closely the spatial information model of both form and process fits what is observed in reality. So that would come into the analysis phase. Now, several project management techniques are prevalent. Some of them which are very relevant, I am trying to highlight some of them, which in many ways are very important when we carry out spatial information projects, the research, the analysis, examination with the help of spatial information. These techniques would be relevant. For example, the first can be the SWOT analysis, which is commonly known as strength, weakness, opportunities, and threats. This kind of analysis. So this technique is used to establish the SWOT as part of the feasibility study in system life cycle approach. So that would be one option when you want to carry out any research activity based on spatial information. The second, as we have discussed earlier also, the rich picture and root definition. These techniques come from soft system methodology. They are used to help system designers determine the scope of a problem. Another can be demonstration system. These are demonstration of spatial information application designed to help users evaluate the system's efficiency. It is used more commonly in the prototyping approach for carrying out any project. Another can be interviews and data inventories. These techniques are used for problem definition, establishing current information, and analysis requirements. Data audits are more structured and also quite valuable in spatial information because it evaluates the availability of spatial data. Another can be the data flow diagram and dictionaries. Now, these techniques are drawn from hard system analysis and represent a more structured approach to system design. They can be of immense value in spatial information for tracking what happens to a data layer through the analysis process. This is extremely valuable in monitoring data quality and providing lineage information. Lastly, the most popular and most commonly used, the cartographic models and entity relationship diagrams. These techniques are of most valuable in structuring the analysis scheme used in spatial information. They help in planning the functional requirements of the analysis. There is another, we discussed it earlier also, the prototyping approach. The prototyping approach developed as a response to the criticism of the system life cycle approach, particularly in response to the lack of consideration of users. The users first define the basic requirement of the system. This could be achieved by using the rich picture and root definition techniques. The system designer takes these basic ideas to construct a prototype system to meet the needs identified by the users. In spatial information projects, such systems are often described as demonstrators. The users who identified the original requirements for the system then experiment with the demonstration system to see if it is what they were expecting. Other potential users of the final system may be brought in at this stage to see if the system is of wider value. The system designer uses their recommendation to further improve the system. So, the prototype approach advantages over the system's life cycle methods on the count. For example, first, users have a more direct and regular involvement in the design of the system. It is easier to adapt the system in the face of changing circumstances, which were not identified at the outset of the project. The system can be abandoned altogether after the first prototype if it fails to meet the needs of the users. This reduces the cost of developing full system. So here you would understand that how the user's requirement is of paramount importance, and this has been given a lot of emphasis in this prototyping approach. However, there are some drawbacks also of this approach. If I can identify some of them, they are, for example, prototyping can be difficult to manage. There may be large number of users. So with large number of ideas and opinions, it would be difficult. The resource implication may change following the development of the first prototype. So then it may also create some situation which may not be very feasible to inculcate in the middle of the project. Now, knowing when to stop development can also be a problem, as we are saying that there might be many number of users. So their differing ideas and opinion, if they are existing, and we are unable to carry forward the project, so we do not know as to when to stop developing this project. So that may also be a problem. All in all, I would say that this prototyping approach, since it has many stakeholders, many users with differing opinion, then this has this inherent drawback flaw which is existing there.